So children, right, let us work now the problems of questions in page number 213. So the first question, children, draw a schematic diagram of the circuit consisting of, so this is the question that we are doing. So right, okay, so that is the question we are doing. So that's the question, right? Okay, schematic diagram of the circuit consisting of a battery of three cells, right, three cells, each of 2 volt, and there are 5 ohm resistor. Then comes the right, okay. So we have a 3 ohm resistor. I mean, sorry, 5 ohm, 8 ohm, and a 12 ohm resistor. Okay, and a plug key. So right, so a plug key, and all of them are connected in series. So we write the solution, right, for the first one. Right, what is that? So we'll draw 3 resistors. Yes, that's a 5 ohm resistor. Then next we have a 8 ohm resistor, and then we have so there's a connection here, and that's a 12 ohm resistor. All are connected to cell to a battery consisting of 3 cells. So of 2 volt, that's 2, that's 2, that's 2. So the total is 6 volt. Okay, right. So these are connected like these cells, right? So that's a positive, that's negative, positive, negative, positive, negative, and there is a plug key, as you said. Okay, so in between there's a plug key, right? Okay, and we close. So that becomes a circuit. So right, children. So this is the first question, right? So the next, so children, right? We will now work the second one. Is the same thing, but here we have to put an ammeter. So there we are putting an ammeter to measure the current through the resistors. Okay, so we have to place an ammeter there. So we'll introduce an ammeter, right? Okay, right. Yes, we'll introduce an ammeter there, right? So how do we do it? So that's it. We are introducing an ammeter, and you know well that ammeter, the way it should be connected. So always remember, children. So the current is going like this. So that's called the conventional current, or the conventional direction of the current. And see that the conventional direction of the current enters the zero side. So that's the positive connected to the positive side, and the negative of the ammeter connected to the other side. So the negative eventually. So that is how we are to introduce. And apart from that, we have to connect what is called a voltmeter. He says voltmeter also there. So okay, where is that? And a voltmeter. So okay, right, okay. A voltmeter also is there. Right, okay, so right there, see that there's a voltmeter there. As you can see, there's a voltmeter connected to the having a potential, okay, right, connected to the 12 ohm resistor. So okay, right, so there is a voltmeter connected, right? Okay, now how do we connect that? So there we are. So we are connecting the voltmeter, and as a positive end, as a negative end of the voltmeter. This is a parallel connection of 12 ohm with the voltmeter. So children, this is the condition. And he asked the question now, what would be the readings in the ammeter and the voltmeter? What would be the readings in the ammeter and the voltmeter? So there it is, we have to calculate now. So how do we calculate it? So observe carefully, children. The current in all the 3 resistors would be same, right? Okay. Now next, and then next we have to calculate how much of voltage is going through V. So now that is what we have to calculate. Simple. If the current and the resistance are multiplied, you will get what is called the potential difference about that, across that. So how do we do it? So we'll do that, children, now. So the total effective resistance. What is the total effective resistance? As all the 3 are in series, naturally the the total effective resistance would be equal to all right, okay, the total equivalent resistance is equal to, that's 5 ohm plus 8 ohm, okay, right, plus 12 ohm. So that will become 5, 8, 13, 25 ohm. So that is the effective resistance. And what is V, potential difference given? That's 6 volts, is it not? So we'll calculate I. I is equal to V by R. Okay, right. So we'll work what is V, children? So it's 6 by 25. So this is the current. So that's the current, okay. Current I is equal to V by R. So, okay, right, how much would that be? So 6 divided by 25. So we'll calculate that. 25, that's 0, 0 0.25 to 50, that's 10, 0, 25, 400. So there we are. So we have calculated that, right? Okay. Just I'll make place for that to be written. So that becomes 0.24 ampere. So that's the current. Now, what is the thing next we have to calculate? So what is the thing that we have to calculate? So we have to calculate the what is that? In the voltmeter, we have to find the now ammeter, the value of the ammeter, the answer, that is 0.24 ampere will be the current that will be flowing, right? And what will be the potential difference here? So potential difference across a 12 ohm resistor. So right, okay. So what is that? So simple, children. It is 12 ohm multiplied by the current that is going inside. So right, we'll go now. Right, so this is ampere reading, ammeter reading, sorry, ammeter reading. That's equal to 0.24 ampere. Now we'll calculate the next one. What is the next one? So we have we have to calculate V across 12 ohm resistor. How do we do it? So we know I in 12 ohm resistor is 0.24 ampere, and the resistance is 12 ohm. So using Ohm's law again, we calculate what is that? V is equal to I into R. So that is, what is I? I is 0.24 into R is 12. So that's 12 4 48, 8 4 12 is 24, and 28. So that becomes 2.88 volt. So therefore, voltmeter reading is equal to 2.88 volt, right? Okay, so that's it, children. This is how we conclude that first answer. So children, right, we'll work the exercise questions from page number 216. Follow carefully, children. I want your attention here. And judge. So you just have to tell the answer, that's all. Judge the equivalent resistance when the following are connected in parallel. So we know well that in a parallel connection, the effective resistance will be less than the least of the resistances of the combination. So naturally, in these two, which is the least? This is 1 ohm and that's 10 power 6 ohm. So naturally, 1 ohm is the least. So the answer would be, what is that? 1 ohm. So it should be less than 1 ohm, right? Less than 1 ohm or 1 ohm, right? Okay. So it should be less than 1 ohm. So that is the thing. So the equivalent resistance should be less than 1 ohm. So that should be the answer. Now next one. Okay, right. The same thing, right? He's asking, but he has given us 3 resistors instead now. So what is that? So 1 ohm, 10 power 3 ohm, and 10 power 6 ohm. Now which one? What would be the equivalent resistance of this? So naturally it will be less than 1 ohm here, because 1 ohm is the least. So less than 1 over that ohm, right? Okay, less than 1. That's it. Good. So we have completed this part. Now we have to calculate the second part. So what is the second question? So we are going to work the second question. What is that? So an electric lamp of 100 ohm, a toaster of resistance 50 ohm, and a water filter of resistance 500 ohm. They are all connected in parallel. So remember, parallel. And to a source of 220 volt. Right, what is the resistance? So naturally the effective resistance is asking in the parallel connection. We are to find, okay, at the same source. That say resistance of an electric iron. So here electric iron connected to the same source. So source is 220 volt. But this electric iron is having the same resistance as these three connected in parallel. So that is these three. So naturally the resistance of the iron will be equal to the effective resistance of 1, 2, and these three resistors. Okay, right. And is asking us, it is taking the same current as all the three appliances. What is the current through it? So we also have to calculate the current through it. Okay, so children, this is the stuff that we have to work. So let us work now this question, right? Okay, so that is we'll work it. So children, so three resistors. Okay, what are the three resistors, children? So let's write R1 equal to 100 ohm, then R2 equal to 50 ohm, and R3 is equal to 500 ohm. So okay, right. So that's what is given to you. The next one, right? They're all connected to potential difference of 220 volts. So this is the source. Now we are bothered about finding out the resistance of the iron, which is having the same resistance as a combination of these three. So they are all connected in parallel. Okay, right? It's given they are all connected in parallel. So naturally, the effective resistance would be the parallel. So naturally, effective resistance, R effective resistance, or let us write it as RP. We are fine. Okay, right. So that would be the resistance of the iron. So naturally, it will be 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So that will be equal to 1 by 100 plus 1 by 50 plus 1 by 500. So okay, finding the LCM, that will be 500. Okay, so this is 5 plus this is 10 plus this is 1. So that will become 5, 10, 16. 16 by 500. Okay, this is 1 by RP. Right, okay. So children, the next. Right, okay. So 1 by RP is that much. So naturally RP will be equal to 500 by 16. Okay, so what will that be equal to? So this is RP is equal to 31.25 ohm. So this is the resistance of the conductor of iron. So that's the resistance of the iron. Now what is the current through it? So current I is equal to V by R, employing Ohm's law. Okay, so because we know well V is equal to IR, right? V equal to IR, so I will be equal to V by R. So what is V here? 220 volts. Okay, right? So that's it. Right, okay. So is equal to V 220 volt and divided by 500 by 16. So that's by 16. Right, okay. So that will become equal to 220 into 16 divided by 500. So that will give me 7.04 ampere. So this is the current through the electric iron, which is having the same resistance as the combination of these three resistors we have seen. Okay, children? Right, that's good. The next, we'll go ahead. So children, right here, let us see very quickly what are the advantages of connecting, what are the advantages of connecting electrical appliances in parallel. Okay, so children, the advantages of connecting electrical devices or appliances in parallel. So all appliances will have same potential difference. All appliances will have different current, and each appliance, okay, can be controlled by different switches, and even if one appliance fuses off or gets switched off, the other appliances continue to work. Okay, right. So children, right, let us work problem number 4. And this problem states that how these three resistors, 2 ohm, 3 ohm, and 6 ohm are connected so that the effective resistance is 4 ohm or 1 ohm. Now, okay, right, so let us work the solutions. There are 2, 3, and 6. Okay, all right. Okay, so children, now we are going ahead. So what is that? So resistances are 2 ohm, 3 ohm, and 6 ohm. How are they connected? How should they be connected so that we get a 4 ohm resistance or 1 ohm resistance? Okay, right. So let me connect it. Say if I try 2 ohm, then 3 ohm, then 6 ohm in series. So this is the first type of connection. So let me call that. Okay. So naturally, I know that there will be the effective resistance will be equal to sum of these three resistances. That is 11 ohm, but that is not equal to 4 ohm. Okay, right. So we have R1 equal to 4 ohm. So that combination is not giving me the 11 ohm, so 4 ohm resistance. Now I try the second one. So what is the second one? So okay, right. I'll try the parallel combination. So of 2 ohm, 3 ohm, and 6 ohm. So 2, 3, and 6. Now okay, let me see whether it will give me either 4 or 4 or 1 ohm. So we know well 1 by R in a parallel will be equal to 1 by 2 plus 1 by 3 plus 1 by 6. Okay, right. I'll work here. So that will be 6 is the LCM. Okay, right. And that's 3 plus 2 plus 1. That will be equal to 6 by 6. That is equal to 1. So 1 by R is equal to 1. So implies R is equal to 1 ohm. So let me call this R2. So what is that, children? So the parallel combination is giving the value of 1 ohm. Okay, right. Let me try another method. So another combination. So I'll try this combination 2 ohm, that is 3 ohm. Then we have the 6 ohm, right? 6 ohm. Now I'll see whether this combination gives me the 4 ohm resistors. Okay, right. How do I do? So okay, children. So if these two are in parallel, so naturally, let me call it Rx. Then effective resistance is Rx. Okay, 3 into 6 divided by 3 plus 6 using the formula. Okay, this is 18 divided by 9. That will give me 2. So equal to 2. So Rx is equal to 2. Right. Now, this Rx and this I can redraw that. That's 2 ohm. This 2 ohm. And that again, the combination is 2 ohm. So naturally, they are in series now. So R3 will be equal to 2 plus 2. That will be equal to 4 ohm. So I got R3. So this combination is giving me the 4 ohm resistance. Okay, children? So there we are. So children, right, let us work the fifth problem. And we'll get for highest and the lowest total resistance. Okay, because of the 4 coils. What are the 4 coils? 4 coils, yeah. 4 coils of 4 ohm, 8 ohm, 12 ohm, and 24 ohm. So, okay, right. So we know well that the highest resistance, we get highest resistance in series combination, and the least resistance uh, in a parallel combination. So naturally, series combination. Okay, what are the resistance to them? So that's 4 ohm. So we have resistances. There are 4 ohm. The next one we have 8 ohm. The next 12 ohm and 24 ohm. So okay, right, highest. So that I'll get in series. Okay, now what is that? So RS, or the highest, will be equal to 4 plus 8. Sorry, that's 4 plus 8 plus 12 plus 24. That'll be 24 plus 24. That's 48 ohm. So that's the highest resistance you get. And what is the least resistance you get? Least. So least will be in parallel. Least will be in parallel. So this is the highest. Right? Okay, that's the highest. And the least, that should be in parallel. Okay? Right. How do we do it? So least 1 by Rp is equal to 1 by 4 plus 1 by 8 plus 1 by 12 plus 1 by 24. Okay, right. So the LCM again is 24. 4 6 plus 8 3s plus 12 2s plus 1. 69, 10, 12. So that become 12 by 24. That will be 1 by 2. 1 by 2. So that is 1 by RP. So RP should be equal to 2 ohm. So that is the least resistance due to the combination of the 4 coils. Okay, right. That's good. So children, right, let us work example 12.10 from your book. So this is to understand that, right? Okay, right. Okay, there is an electric iron which when it is at the highest, okay, connection or highest setting, it consumes it has a power of 840 watt, and when it is at the minimum rate, so when it is at the minimum rate, it is 340 watt. 360 watt, right? Okay, both of them, the iron is operated at a voltage of 220 volt. What are the current and the resistance in each case? What are the current and resistance in each case? So let us see, children. So let us work. So when the device is taking the maximum power, okay, like maximum power, so we work maximum power. Then next it is minimum. So when it is working at minimum power. Okay, right. So what is that? So power is given to us. So it's 840 watt. The next one, the potential difference, the source is 220 volt source. Now he's asking us to calculate what I is and R is for this condition. The next one, what do we do? So we know well that power is equal to potential difference into current. So I can calculate current. How? I is equal to P by V. So what is that equal to, children? P. What is P? 840 by V 220. So if at all I calculate that, then I get a value of right. Okay. So just I can find out what the value is. Okay. Right. And the value is right. Okay. So 840 divided by 220. So that'll give me 3.81. So, okay. That's 3.81 ampere. Okay, that's good. Now, what is the resistance? Okay, what is the resistance? So I'll write this here, I equal to 3.81 ampere. Now let me calculate the resistance. Now what is R? R we know well is equal to R equal to V by I. So what is the V? It's 220 by I. What is the I which I have calculated? So it's 3.81. So when I divide it, so I'll just check, right? Okay. So that's 220 divided by 3.81. That will be equal to 57.7. Right? So it is 57.7 ohm. Okay, right. So that is the resistance and the current at that condition. And the next one, do the same thing here also, children, for minimum power. So power is equal to 360 watt. Okay, so V here again is 220 volts. Okay, right. So again we have to calculate I and R for this case. So what is I? So again P is equal to V into I. Okay, good. I will be equal to P by V. So that will be 360 divided by 220. So let us see I. Right. Okay, what is I there? Right. So that is 360 by 360 divided by 220. That will give me 1.63. So that is 1.63 ampere. Now let us calculate resistance R equal to V by I. What is V, children? What is V? V is 220 volt. I so we calculated 1.63. So okay, right. So what is that? 220 divided by 1.63. So that is equal to 134.96. So that's 134.96 ohm. So thus we have calculated the respective or the corresponding resistance also. So this is it, children, right? Now we'll move to. So children, right, we'll understand now example 12.11. So there is 100 joule of heat produced in each second in a 4 ohm resistance. Find the potential difference across the resistor. So what is that? 100 joule of heat is produced in every second. So the power, the rate at which the heat energy is released. So that is the power of the heating device, you can say. So power is equal to 100 joules of energy produced in 1 second. So that is 100 watt. That's the power of the heating device. And the next one, what is the resistance? Resistance of the device is 4 ohm. And find the potential difference across the resistance. So we have to calculate V. So we know well that power is potential difference voltage into current. So I want V. So I can convert by Ohm's law V by R. Okay, right? So I'll be V square by R. That is power. So I want V. So V square equal to P into R. Right? Okay. So that'll become V square is equal to what is P? P is given, and we also have R here. Right? Okay. So that is P into R. So P into R. That is what is P, children? So it is 100 into what is R? 4. So that becomes 400 as V square. V equal to square root of 400. That will become 20 volt. So that's V. So thus we have calculated the potential difference for this problem, right? So children, right now we'll work. So we have already worked this problem. So children, right? Okay, we have come back, and we'll work now this problem. Right. So that is example 12.12. Right. Okay. Electric bulb is connected to a 220 volt generator source, and the current is 0.5 ampere. So that's voltage given and the current given. What is the power? So simple. Actually, the answer is very simple. So what is that? So it is given as voltage 220 volts and the current I is equal to 0.50 ampere. So you have to calculate the power. How much? So right. Power we know well is equal to voltage into current, that is equal to 220 volts into 0.5 ampere. So that will be equal to, so 220 into 5 by 10, that's 1. So it becomes 110 watt. So unit of power is watt. Okay, so children, there we are. So children, right, we'll work the questions in page number 218. All right, the first question: why does the cord of an electric heater not glow while the heating element does? So, okay, children, look here. The electric heater's cord of the electric heater is made up of copper wire, so which has low resistivity. Low resistivity. Okay, so its value is less resistivity, and second thing is it is also thicker than the element, thicker than the heating element. Okay, so that is the thing, right? Okay, the next we move to the next part. All right, okay, so that's it. We'll work the remaining later in the next video. So just limit ourselves to this today, right? Okay, right. Thank you very much.